Hello viewers, in the last session we have seen the theorem on counting zeros of an analytic function inside a closed curve, and we have seen as a consequence the Rouché's theorem or one version of Rouché's theorem, and we used that to prove the local version of maximum modulus theorem. We used the counting zeros theorem to prove the local version of the maximum modulus theorem. So, today we are going to see yet another consequence of the theorem on counting zeros, an important one, a very important one, namely the open mapping theorem. So, first I will begin with stating the global version of the maximum modulus theorem, and instead of proving it directly, I will take an indirect route. I will prove the open mapping theorem and show that the maximum modulus theorem, the global version or the local version, can also be seen as a consequence or a corollary to the open mapping theorem. Okay. So, I will take that route. So, we need to build some tools before that. So, firstly let me begin by stating the global version of the maximum modulus theorem. Okay. So, maximum modulus principle. Okay. So, let G be a bounded region and let F be analytic on or let me say in G and continuous on the boundary. Okay, continuous on the closure, actually on the whole closure of G. Okay. Closure of G. So, recall that is denoted by G bar. Okay. So, then the modulus of F attains its maximum on the boundary of G. Okay. So, recall we denote the boundary of G by dou G, okay, which is the closure of G minus the interior of G, which is G itself, because G is a region. Okay. So, the maximum of modulus of F is attained on the boundary of G. So, that is the statement of the maximum modulus principle. So, as I said, we can directly use a topological argument and use the local version of maximum modulus theorem to prove this principle. Okay. But what we are going to do is we are going to develop tools for proving the open mapping theorem as a result of the counting zeros theorem. Okay. And then we will see the proof of this maximum modulus principle as a consequence. Okay. So, recall. So, in that direction we will recall something. So, recall the index of a closed curve with respect to a point. So, sometime when discussing Cauchy's theorem or various versions of Cauchy's theorem, we had the concept of the index of a closed curve with respect to a point. Okay. So, what this was as follows. We defined the index of okay. So, let me recall the lemma which actually had said something. Okay. So, if gamma is a piecewise differentiable closed curve, okay, we can prove using a smooth curve. We can prove the lemma using smooth curve and generalize it to piecewise differentiable closed curve like we have seen earlier. Okay. So, few points or a finite number of points on the curve having I mean where gamma is not differentiable will not actually affect the proof of this lemma. Okay. So, if gamma is a piecewise differentiable closed curve, not necessarily simple, that is important. Okay, which does not pass through the point A. Okay, A belongs to C. Okay, then the value of the integral of the contour integral integral gamma dz by z minus a is an integer multiple of 2 pi I. Okay. So, this lemma we proved some time back, okay. And then based on this lemma, since this integral evaluates to an integer multiple of 2 pi I, we named that integer as the index of gamma with respect to A. Okay. So, we defined based on this lemma n gamma A, okay, to be 1 by 2 pi I. So, n gamma A is an integer which is defined to be 1 by 2 pi I times the integral contour integral over gamma of dz by z minus a, okay, called n gamma A is called the index of the closed curve gamma with respect to A. Okay. This is also called as winding number, okay, owing to the geometric significance that if A is the center of a circle or if A lies inside a simple closed curve, okay, then the index of that circle with respect to the point A is 1 times 2 pi I, or if you have a circle which goes around n times. So, if you have a parameterization of a circle which goes around the point A n times visually, then the index of that curve gamma which goes around n times with respect to the point A is n, is the integer n. Okay. So, owing to that geometric significance, also called n gamma A is also called winding number. So, that is suggestive of the geometric significance of gamma with respect to A. All right. So, some properties are in order. Okay. So, properties of n gamma A. So, once again the assumptions are that gamma is a closed curve which does not pass through the point A, okay, and it is a piecewise differentiable curve as well, gamma. Okay. So, then the properties of n gamma under these assumptions: 1, n gamma A is equal to, or n minus gamma A rather, is equal to minus of n gamma A. Okay. That is the first property. Second, if gamma lies in the inside of a circle, recall we made that notion very precise what the inside of a simple closed curve is. So, in this case we take a circle and if we assume that gamma lies in the inside of a circle, okay, then n gamma A is equal to 0 for all points A outside of the circle. Okay, 3. So, for 3, let us notice that when you have a closed curve. Okay. So, before stating 3, let me make a remark. Okay. So, this is a remark. Gamma is a closed curve. What that means is our closed curves are functions from intervals to the complex plane, and we are calling the image of gamma as the trace of gamma, gamma star. Okay. So, gamma star is a closed and bounded set in the complex plane. Okay. So, C minus gamma, so it is a compact set in C. So, C minus gamma is gamma star, okay, is open in C. So, what that tells us is that C minus gamma star, okay, is actually divided into components, okay, which are the maximal open sets whose union is C minus gamma star. Okay. So, so here is a visual example. Suppose this is your gamma star in C, then you have component 1, which is this open set, which does not include the boundary. Okay. And then you have component 2, which is right here, the hashed area. Okay. And then there is the component 3, which is sort of outside the visual boundary here. Okay. So, which is everything else in C minus gamma star. Okay. So, it is the unbounded component. Okay. So, this is a visual example, but we can say that C minus gamma star is an open set. So, it is a union of its components. Components, recall, are the maximal open sets, maximal open connected sets. Okay. So, you take the connected component containing a point in C minus gamma star, okay, and then take the maximal such, okay, and then form their union, and then you get C minus gamma star. Okay. And on these components, so property 3 says that, before that I will also want to say that, so gamma is set to determine the components of C minus gamma star. Okay. And exactly one of these is unbounded. Okay. Of course, it is a compact set. So, I mean gamma star is a compact set in C. The complement of it will contain some points which have very large modulus. Okay. So, take because a compact set is bounded. Okay. So, you take a point which is very far off from the origin in terms of modulus, and then you take the connected component containing it, and it is exactly 1 because you are anyway collecting the connected component containing points which have very large modulus. Okay. All right. So, so it is unbounded, and here is the third property, n gamma a is constant, okay, is constant function on components of C minus gamma star, and is 0 and is the 0 function on the unbounded component. Of C minus gamma star. Okay. So, what that means is n gamma a can be different constants on different components, but on a given component it is a constant function. Okay. So, that is what is the meaning of this statement. Okay. So, so here is the proof of these properties. Well, the proof of 1 and 2 are fairly easy. The proof of 1 is that n minus gamma a, recall what minus gamma is, it is not minus gamma of t for t belonging to the interval 0 1. Okay. It is the inverse, I mean it is gamma star traced in the opposite direction. Okay. So, recall that. So, this is equal to 1 by 2 pi I, by definition integral over minus gamma of 1 by z minus a dz. Okay. So, gamma is being traced in the opposite direction from the ending point to starting point for gamma. Okay. So, that is minus gamma. So, by definition we already captured this property, this is equal to minus 1 by 2 pi I of integral contour integral over gamma of 1 by z minus a dz. Okay. And this is precisely minus of n gamma a. Okay. So, that is easy, that proof is easy, and also property 2, the property 2 can be proved easily. Okay. So, if gamma lies on the inside of a circle, okay, gamma belongs to the eye of a circle, okay, then for any a belongs to outside of circle of that circle, okay, 1 by z minus a is analytic. Function inside the circle. Okay. Okay. I on the disk, the interior of, which is the interior of eye of circle. Okay. The interior of the inside of a circle is a disk, and by the disk version of Cauchy's theorem we know that, and by the disk version of Cauchy's theorem we know that integral over gamma. Okay. So, any closed curve gamma, okay, of 1 by z minus a dz is equal to 0. Okay. All right. So, that is the proof of property 2. Property 3, gamma star is compact. Okay. So, so let A and B belong to the same region, I mean to say the same component of C minus gamma star. What I want to show is that n gamma A is equal to n gamma B. Okay. So, so I am going to use the topology of the component. So, recall that if you have a component, the maximal connected set, open connected set, then given any 2 points in this component, there is a polygonal path connecting these two. Okay. So, that is from the topology of the complex plane. Okay. So, using that fact, so there is a polygonal path connecting these particular A and B. Okay. So, if I can show that n gamma of x is a constant on a straight line segment, then you can extend this fact to the polygonal path and claim that n gamma x is constant for any polygonal path altogether. Okay. So, then I can conclude that n gamma A is equal to n gamma B. Here is the path that I will take. So, there is a polygonal path connecting A and B lying completely in the component. Of C minus gamma star containing A and B. Okay. So, the point is it is clear of gamma star, it is the polygonal path does not intersect gamma star. Okay. So, i.e. This path does not intersect gamma star. Okay. So, it is enough to show that if A and B are joined by a straight line, connecting A and B, which does not intersect gamma star, okay, then n of gamma A is equal to n of gamma B. So, outside the segment joining A and B, this is a standard thing that one does, z minus A divided by z minus B, the complex number z minus A divided by z minus B for z outside the segment A and B, okay, is never real and less than or equal to 0 simultaneously. So, here is A B, if we take a straight line joining A B, okay. So, z minus A by z minus B takes, okay, the map z minus A divided by z minus B takes B to infinity, okay, and then it takes A to 0. So, we have a line joining 0 and infinity. Well, it actually takes this line, this map f of z equals z minus A by z minus B, takes the line segment joining A B to this negative real axis, to this whole negative real axis. Okay. So, if we ignore the line segment joining A and B, okay, the points outside it are precisely mapped onto the complement of the negative real axis via the map z minus A by z minus B. Okay. And we know that when we remove the negative real axis, we can define a branch of logarithm, an analytic branch of logarithm on the complement of the negative real axis. Okay. So, that is the point. So, so what we will do is, so the principal branch, you can take a branch of logarithm, analytic branch. Okay. So, I will take the principal branch of logarithm of log z minus A by z minus B, okay, is analytic on the complement of the line segment joining A and B. Okay. So, since this principal branch is analytic, we can differentiate it and we know what its differentiation is. D by dz of log z minus A by z minus B is your 1 by z minus A. So, log z minus A by z minus B, I am writing that as log z minus A minus log z minus B for all z in the appropriate place. Okay. So, then this is the differentiation of this is 1 by z minus A minus 1 by z minus B for z belongs to the complement of the line segment. Okay. So, I will just use a shorter notation, I will just say the AB C minus AB. What that means is the complement of the line segment joining AB. Okay, I am just using a shortcut. Okay. So, then gamma does not meet the segment. Okay. So, gamma star does not intersect. So, recall we are being sloppy about gamma and gamma star. What I mean by that is we agreed that we will confuse between the curve itself and its trace. Okay. So, I will write gamma star or gamma. Okay. Gamma star does not intersect this line segment joining A B. So, the integration over gamma of 1 by z minus A minus 1 by z minus B, okay, which has an antiderivative. Now, the integrand has an antiderivative in the region of interest. So, if you take any closed curve in that region, okay, which lies entirely in the region, you know that by the antiderivative theorem this has to equal 0. N gamma A is equal to n gamma B, right, because this is also integral over gamma 1 by z minus A dz minus integral over gamma 1 by z minus B dz, and each of these are 2 pi I times the index of gamma with respect to A or B. Okay. So, this is okay. So, these are equal. Okay. So, that proves property 3. Okay. Also, I claim that the unbounded component has 0 as its index. Okay. So, if A is sufficiently large, okay, then gamma is contained in the interior of circle of radius rho, where rho is strictly less than the modulus of A. Okay. Then by the earlier property that if gamma lies in the interior of a circle, then for points outside the circle this is 0, I mean the index is 0. Okay. Then we have that the index of gamma with respect to A is 0 definitely, okay, by 2. And since we just proved that the function n of gamma x is constant on components of C minus gamma star, the value of n gamma A for any point A in the unbounded component has to be 0. Okay. So, n gamma A, okay, I will say B is 0 for any B belongs to unbounded component of C minus gamma star. All right. So, that is the property, okay, properties of this index. Okay. So, now we are going to use this index and try to sort of reinterpret the counting zeros theorem, okay, and we will see that that interpretation has good consequences. By counting zeros theorem, okay, we had that if gamma is a simple closed curve, okay, then the integration, the contour integration over gamma of f prime of z by f of z, okay. Of course, gamma is contained, should be contained in region of analyticity. Okay, I am not going to state this precisely, but you already had this statement of counting zeros theorem. So, I will say that if gamma is a simple closed curve contained in the region of analyticity of f, okay, then integration over gamma of f prime z by f of z dz, okay, gives you 2 pi I times n, where n is the number of zeros of f inside gamma counting multiplicity. Okay. So, all right. So, by considering the map, okay, so consider the mapping W equals f of z. Okay. So, then d w will equal f prime of z dz. Okay. Also, let capital gamma be the map of, okay, be the map gamma, okay, so composed with f. Okay. So, so capital gamma is a curve, okay, is a closed curve now, right. Gamma is a curve and f maps gamma, the simple closed curve gamma to somewhere else. Okay. So, capital gamma is a closed curve in the image of f. Okay. It's contained in the image of f. Okay. So, so this left hand side, okay, this left hand side integral over gamma f prime z dz by f of z can be reinterpreted as the integration, contour integration over capital gamma of dw by w, okay, that is now equal to so by substitution really, okay, this contour, this new contour integral is equal to 2 pi I times n. Okay. But so, rewriting this is 1 by 2 pi I times integral over gamma of dw by w, okay, which is nothing but the index of capital gamma with respect to 0. Okay. So, this is a very useful interpretation. Okay. So, it tells us that the index of the target curve, okay, with respect to 0, target curve via f of little gamma, okay, with respect to 0 gives actually the number of zeros of f inside little gamma. Okay, this is very useful. Okay. So, this is just the reinterpretation of that counting zeros theorem, but we will put this to use. Okay. So, let what we will do is let A be an arbitrary complex number. Okay. So, let A belong to C, I will just say A belongs to C, okay, and apply counting zeros theorem to the function f of z minus a. Okay. So, the zeros of firstly the zeros of f of z minus a are the solutions to the equation f of z equals a. Okay, f of z minus a equals 0 implies f of z equals a. So, the number of zeros, okay, of f of z minus a inside a circle, let us say a simple closed circle gamma, okay, counting multiplicity, okay, is say m, call that m, this is integral over gamma of g prime of z divided by or rather I am using f. Okay. So, this is 1 by 2 pi I, okay, times f prime of z divided by f of z minus a, because the derivative of f of z minus a is f prime of z still. Okay. And this we said is the index of capital gamma with respect to the point A now, okay, where capital gamma is f circle little gamma. Okay. So, where we use the simple closed curve, we use a simple circle around A. Okay. So, so we have that. Okay. So, if A and B belong to the same region, okay, same component actually determined by capital gamma, okay, by property 3 above. So, we know that the index function is constant on components. So, if we pick 2 points in the components determined by capital gamma is also a closed curve. So, it determines some components. So, if you pick 2 points in the complement of capital gamma star, then you know that the index of those 2 points has to be equal. Okay. The interpretation here is that the number of times f of z takes A will have to equal the number of times f of z takes B. Okay. It might not take A at all. So, in which case it will not take B at all. Okay. So, but the number of times it takes A should equal the number of times it takes B. Okay. So, by property 3 above, we know that n gamma A is equal to n gamma B. Okay. So, that has an interpretation that and so the number of zeros of f of z minus A, okay, inside little gamma is equal to the number of zeros. I will just put hash of zeros of f of z minus B inside gamma. So, said otherwise, the number of times f takes A inside gamma, little gamma, should be equal to the number of times f takes B inside little gamma. Okay. So, of course, counting multiplicity. Okay. So, now here is a theorem which is okay, from which the open mapping theorem will follow. Okay. So, suppose that f of z, okay, f is analytic at z naught. A function f is analytic at a point z naught, okay, and f of z naught is equal to w naught, and that f of z minus w naught, okay, has a 0 of order n. At z naught. Notice that when I say that f has a f of z minus w naught has a 0 of order n, I am automatically assuming that f of z is not identically w naught in a neighborhood of z naught. Okay. So, it has a 0 of order n finite. Okay. So, if here is the conclusion, if epsilon naught is sufficiently small, okay, then there exists a corresponding delta positive, okay, such that for all A with modulus of A minus w naught strictly less than delta, the equation f of z equals A, okay, has exactly n roots inside the disk modulus of z minus z naught less than strictly less than epsilon. Okay. So this is a very important theorem. Okay. It says that there is some delta around W naught. Okay. There is a delta neighborhood of the W naught. Okay. So, which is mapped onto by a subset of a neighborhood of Z naught. Okay. And in such a way that it is an n to 1 correspondence, if the where n is the order of the 0 at Z naught of f of z minus W naught. Okay. So, f of z minus W naught is definitely 0 at Z naught. Okay. So, if n is the order of 0, then any there is a small neighborhood around W naught, such that any point in that neighborhood is actually taken up by f in some neighborhood of Z naught. Okay. And then it does so n times exactly. Okay. So, I will sort of draw a picture to elaborate that. So, here is W naught, okay, here is Z naught. So, there is a small, the claim is that, the theorem claims that there is a small neighborhood, delta neighborhood of this is delta, such that if you take any point here, okay, then there are exactly n pre-images counting multiplicity. Of course, you have to entertain multiplicity. There are n pre-images here, which all map to that point, where n here refers to the order of 0 of f of z minus W naught. So, this is interesting. So, here is the proof. I mean, as a consequence, we will actually have the open mapping theorem, because now we can say that if you take Z naught and the target W naught via f, okay, then there is a open set around this, there is a neighborhood around this, such that you have a you have something from here, from the neighborhood of Z naught, which is mapped to this neighborhood. Okay. So, every point in this is a target from the neighborhood of Z naught. Okay. So, that actually gives the open mapping theorem. Okay. So, let us see the proof of this theorem. So, we saw that the zeros of an analytic function are isolated of a function which is not identically 0, okay, are isolated. Okay. So, the 0 of f of z minus W naught is also isolated. So, the 0 of f of z minus W naught at z naught is isolated. So, there is an epsilon positive, okay, such that f of z, f is defined and analytic on modulus of z minus z naught strictly less than or equal to epsilon. Okay. So, this is better said as b z naught epsilon bar. Okay. So, by contracting that the neighborhood of the isolated 0 enough, I can assume that there is a closed disk inside, inside on which f is defined and analytic. Okay. So, f is defined and analytic on that, and z naught is the only 0 of f of z minus W naught in b z naught epsilon bar. Okay. So, what that gives is let gamma be a simple closed curve whose trace is, okay. So, let gamma be the curve, I will just say the curve modulus of z minus z naught is equal to epsilon. So, it is a circle of radius epsilon around z naught, okay, oriented positively, we will assume oriented positively. that does not matter for us, but what we will do is now let capital gamma be the image of gamma star, okay, under f, okay, under the mapping W equals f of z. Okay. So, since W z naught belongs to C minus gamma star, of course, W naught will belong to C minus capital gamma star. Okay. So, and since this is open, okay, there is a neighborhood of W naught which is in C minus gamma star. Okay. So, there is a delta positive such that W belongs to C minus gamma star for W belonging to a ball of radius delta around W naught. Okay. So, this is our candidate which we are seeking. Okay. So, now if you take any 2 points in this ball, since this ball is clear of gamma star. So, there is no intersection of this ball with gamma star, then by remark above, okay, f takes A and B, okay, the same number of times. Okay. What was the remark? We said that n capital gamma A. Okay. So, I should complete this inside, I will say inside of little gamma. So, we said that n gamma A is equal to n gamma B, n I mean the index function on the components of determined by capital gamma is a constant function. Okay. So, n gamma A is equal to n gamma B for A B belonging to the same component determined by capital gamma. So, in particular when they are in this ball, they are in the same component. Okay. So, n gamma A should equal n gamma B. Okay. So, this happens, but we know a specific point which is already in this ball, namely W naught. Okay. But since the order of but since the value W naught is taken by f n times, okay, every value A belongs to B W naught delta is taken n times by f inside gamma, okay, counting multiplicity. This is exactly what we wanted. Okay. So, that is the conclusion. F of z equals A has exactly n roots inside the disk. Modulus of z minus z naught is strictly less than epsilon. Okay. The inside of gamma is nothing but, inside of little gamma is nothing but the interior of the disk, which is precisely this region. Okay. So, that is the conclusion. Okay. So, that completes the proof of this theorem. One more remark. Okay. So, the zeros of f prime are isolated. Since f prime is also, when f is analytic, f prime is also an analytic function. So, the zeros of f prime are isolated if we choose epsilon, so that f prime is non-zero in 0 strictly less than mod z minus z naught strictly less than epsilon. Okay. Then the roots of f of z equals A, okay, for A not equal to W naught, okay, are simple, i.e., f of z equals a does not have a 0 of multiplicity 2. In 0 strictly less than mod z minus z naught is strictly less than epsilon. Okay, so, that follows from Taylor's theorem using local power series expansion, if you like. Okay. So, we will see some consequences of this theorem next time. I will stop here.